Yeah, please type in the chat box. Am I audible? Good morning, guys. Yes, it's audible, right? Is it audible? Audible. Okay, thank God. So I guess when I was, putting on the system, it started updating actually. It's an unplanned update actually suddenly, so it was taking some time. Yeah. Okay. So all clear? Fine then. Okay. So we will start the session straight away. In today's lecture, we will talk about buoyancy and also differential analysis of fluid systems actually. Okay. Now, in case of buoyancy, we know that buoyancy is basically the net upward force exerted on the bodies, and we will see why there is actually a net upward force acting on that bodies, and also differential analysis of fluid systems actually. Okay. So in differential analysis of fluid systems, we will see if you want to analyze any flow, there are two particular ways in which you can analyze any flow. One thing, whenever there is a flow happening, you can pick a small differential element in the flow and you can start the analysis, or else you can actually take the complete fluid and you can do the control volume analysis. Okay, so there are two ways in which you can do. So we will actually look at the first case in this differential analysis of fluid systems actually. Okay, so anyway, if you go for the topics, we'll have buoyancy, this concept of meta center, basically stability of this buoyancy, and also we will look at differential analysis of fluid systems actually. Okay, and we will also solve a bit of numericals on these things. So first of all, before going straight away, let us solve a question from curved hydrostatic forces, because in yesterday's class we have solved questions on plane surfaces. We can solve this question on curved surfaces actually. Okay, so let us solve this. So see, a 30-ton 4-meter diameter hemispherical dome on a level surface is filled with water as shown in figure. Someone claims that he can lift this dome by attaching a long tube to the top and filling it with water. The required height of the water in the tube to lift the dome is dash meters actually, round up to 2 decimal places. Disregard the weight of the tube and the water in it. So practically what's happening here, there is a heavy dome. So there is a 30-ton dome actually sitting here. Now by attaching a glass tube to this, we are actually filling water in this. Okay, so when you fill water in this, what happens actually? Look, this height is h. So first of all, let us try to understand the physics that's happening here. If this height is h, then because of pouring water, the pressure at this point, the pressure acting at this points, the pressure acting at this points will increase. Yes or no? As this h is increasing, as you keep on pouring the water, as this h increases, the pressure acting on the inner surface of the dome will actually increase. Correct? Is the concept clear till here? So please type in the chat box. Basically, in order, if you see, if this is the height h, as you keep on pouring water, as this height increases, the pressure acting at all these points will actually increase. Correct? So there comes a particular situation where the pressure acting on the dome is actually balanced by the weight of the dome, so that this contact at the dome and level will actually get disconnected. Yes or no? Means basically, if you start if you keep on pouring water, then this dome, there comes a moment at a particular point where this dome will actually lost contact. It's not like you can completely lift the dome, but until this contact, means until this water is stored here, this dome will just get lifted up from this particular flat surface. Okay, now they are asking what should be this water level h so that this dome can be lifted. Okay, so now let us see. For lifting of the dome, weight should be actually balanced with the hydrostatic force. Actually here. Okay, so hydrostatic force. Now if this weight is actually equal to hydrostatic force, then try to understand one thing. If I have a dome like this, for example, let us mark it. Okay, fine. So let us suppose, so let us suppose there is a dome like this. Okay, for example, Fine. Okay, so there is a dome like this. Then having hydrostatic force here at this point, like this, means having fluid here and P ATM here. To calculate this force, we can actually assume that if there is a dome like this and if there is a fluid here, and obviously if there is atmosphere here on this part, the magnitude of the hydrostatic force acting on the dome will be equal in both these cases, correct? Yes or no? The magnitude of the let us suppose if this pressure is due to a column H, then you can actually have a fluid of column H actually. You can actually have a fluid of column H actually. So in these two cases, the hydrostatic force acting on the dome will be equal, but of course they are in opposite magnitude. In this case, it will be acting in the upward direction. In this case, it will be acting in the downward direction. That's it, right? So if I want to calculate the magnitude of hydrostatic forces, what I can do? Weight should be equal to weight of, weight is equal to, you can see, you can erase this, and what you can do is actually, if you neglect the small diameter of the tube, for example, if you keep a small fluid column of height H, for example here, so you can see this is a column of height H, R plus H actually, okay, so you can see this is actually a column which is like this. Fine. Now we all know that this is R. From here to this location, this is small r, okay, so here to here this is small r, and here to here there is H like this actually here, okay, this is H obviously. Now if this is hemispherical dome, the weight or the hydrostatic force is equal to weight of this particular fluid which is supported by this particular dome, correct? So you can see, if you hatch it, is equal to weight of, magnitude of weight of fluid supported by the hemispherical dome, by the hemispherical dome actually, okay, so this is by the hemispherical dome. Now you know, obviously the base of this spherical surface is actually cylinder, circle, okay, so the base of this hemispherical dome is actually a circle. If you project this circle onto the top up to this height R plus H, can anyone tell me what is this cross section? This is a circle again, correct? Because if this is a circle, then obviously the projected area, or basically the volume of fluid supported by this particular hemispherical shell will be like a cylinder, yes or no? Now what is this particular volume? So weight of dome is equal to, which is 30 tons, so 30 into 10 cube into G obviously. So this is equal to density of the fluid into G into this particular volume. And what do you get for that particular volume? Look, initially this is completely a cylinder. If this radius, if this diameter is a D for example, then you can see this complete volume is actually pi by 4 D square times R plus H. So this is the total volume of the cylinder minus, what we can do, we can subtract the volume of this hemisphere, yes or no? So what is the volume of hemisphere? Pi d cube by 12, because complete sphere is pi d cube by 6, so this is pi d cube by 12. Is this expression clear to all of you? So please type in the chat box, is this expression clear to all of you? Did you all understand how we have written this? Basically this is the shaded portion of the volume, correct? So density into G into this total volume of the cylinder of height R plus H minus this cylinder of, this hemisphere of volume pi d cube by 12 actually, okay. Now if you do these calculations, then let us see, D is how much they have given you? D is actually 4 meters. So if D is 4, then obviously radius is equal to 2 meters, okay. Now you can cancel this G, and this is water, so water can be taken density 1000, they haven't given any value. So 30 is equal to pi by 4 times of D square, so 16 into R plus H, so 2 plus H, we don't know what is this H, minus, if you take pi by 4 common, d cube 64 by 12 actually here. Okay, so let us simplify this value actually. So 4 table 3 and 4 table 16 times obviously. So this 4 can cancel this 4 and a 4 here. So 30 is equal to pi times of 8 plus 4h minus 4 by 3 obviously. Okay, so then let us simplify this. 8 minus 4 by 3, 8 minus okay, if you take LCM for example, so 30 is equal to 5 times of 3 8s are 24 minus 4, 20 by 3 plus 4h by 3. Okay, so h is equal to 90 by pi, or 1 by 4 times of 90 by pi actually. So 90 by pi minus 20. This is the answer. So if you simplify, you will get the answer in certain meters. Okay, so let us check what is this answer in meters actually. So let us do some calculation. 90 by pi minus 20. Okay, so this is the value divided by 4. 2.161 meters is what you're getting. Yes. So in last term denominator is 3. Where here in this term is what you're telling. Normally if you take the volume of sphere, we have 4/3 pi r cube, which can be written as 4/3 pi into diameter cube by 8. Okay, so for the full sphere it is pi d cube by 6. Okay, so for the full sphere it is pi d cube by 6. So half of that is 1/2 into this is actually pi d cube by 12. Okay, because pi by 4 is common, we have taken pi by 4 common. Yeah, if you take pi by 4 common, then what happens? It should be 3, no? So in last term denominator is 3. If U-tube diameter is given, then we have to subtract obviously, but U-tube diameter is not given, so it's very small diameter. Okay, compared to 4 meters is like very large heavy spherical dome. It's a 30-ton dome, but out of that, if you have a small tube, so we can neglect that. Okay, is this calculation correct? Because you can see, obviously if you take pi by 4 out, here you will have a 3. Okay, so 4 3s are 12, correct? So calculation wise, is it clear to all of you? And conceptually, both? D by 3 is term remaining after taking pi by 4. Yeah, obviously it's pi by 3 now, if you take 4 out. Okay, third step, 1 2 3. This 3 is here, still continuing. In third step, what happened? 30 is equal to pi by 4 into 16 times of 2 plus h minus 64 by 12. So this 4, 12 table actually, or 4 table you can cancel 4 this 3 times and this 16 times. Then using this 4, we have calculated this 16 4 times, this 16 4 times, and 8 plus 4h minus 4 by 3. Okay, here I think you are telling, right? If you take 4, okay, got it. Yeah, basically here what they are telling is, if this is pi by 4, if I take pi by 4, we have actually d cube by 3 actually is what you are telling, correct? Pi by 4 times 16 actually. Okay, so this is the correct equation. It should be 3. That's what you are telling. If you take 4 out, you have a 3 before cancellation itself. Okay, yes, correct. Okay, so then you can see this is 64 again. 64. Then you can perform this calculation. So 4 and 16. Okay, so if you simplify this, then 30 is equal to pi times of 8 plus 4h minus 16 by 3 is what you are having. So 30, h is equal to 1 by 4 times of 30. If you take LCM, this is 30 by 3, so 90 by pi minus, actually if you take LCM, 24 minus 16 is 8, so 4h minus 8 or 12h minus 8 by 3 completely. So this is, let us do the simplification in a bit, no need of direct calculations. So let us do one more step. Pi times of 3 8s are 24 minus 6, 8 plus 4h by 3. Okay, so 8 plus 12h by 3. Okay, so 8 plus 12h by 3 obviously. So h is equal to 90 by pi. So 90 by pi times of 90 by pi times of 1 by 12 times 90 by pi minus 8. Okay, so this is the correct expression. So 90 by pi minus 8, 90 by pi minus 8 divided by 12. Okay, so 1.72. Yeah, 1.72 meters is the correct value, because this 3 we have taken one excess common. Correct. Yes, 1.72 meters is the correct answer. Yes, basically when we are taking this 4 common, this is the 3. Yes. Today when class started late now, obviously that disturbance in the mind is there ultimately. Okay, because we were starting to setting up everything by 7:25 and all, but suddenly it started updating. Okay, but it's a nice question actually. You can understand, to lift the dome, just if you punch a small hole and if you start pouring water, you can just make this contact get lost actually. Okay, so this can happen. Fine. So did you understand this? In yesterday's class we have solved one question on this covered surface having a spring pushing force. So we have calculated F spring, and in the other case we have actually seen how to calculate the hydrostatic force on a spherical surface. Okay, so both these are actually nice questions. Fine. So in today's session, let us start our discussion on, so basically in the last lecture we have talked about a bit of hydrostatic forces actually, and in today's class we will actually look at this concept of buoyancy and flotation. Okay, so let us see how we can talk about this buoyancy and flotation. For example, if you have any body, and let us suppose if this body is in fluid, for example, is in expanse of a fluid, then for example if you take a small section along the body, like for example small section of diameter d or some cross section. Okay, so let us suppose you take certain cross section, some small cross section here. So let us suppose this is a dA and this is also dA, and this is Z for example, because this Z will change depending upon the location where you change. So this is Z actually. So this is Z. Then we know the pressure acting at this point is P. For example, let us suppose if this top edge is at a height H, then the pressure acting at this location is actually P. The pressure acting at this location is P, and here it is P plus rho fluid Z Z actually. Yes or no? So at this point, because if this height is Z, then definitely the pressure acting on this particular element is P plus OFGZ, and if this elemental area is dA on this particular block, if you talk only the hydrostatic force, okay, I'm not talking about the weight of the body. If you are talking only the hydrostatic force, net hydrostatic force is, you can see P plus rho F G Z dA minus P times of dA actually. Okay, so this is P times of dA. P and this PdA gets cancelled, so you can have rho F G Z into dA, and you can clearly understand rho F Z, this Z into dA is nothing but this small elemental volume inside the body. Yes or no? So this small elemental volume inside the body, so which is dV. So therefore total hydrostatic force on the body, is equal to integration over this dF. For example, if you call this dF, this is equal to integral over rho Fg dV actually. Okay, and clearly if this is a volume integral, then rho Fg is a constant and integration of dV is nothing but volume, which is actually present inside the fluid, volume submerged. Okay, because we have seen whenever you are writing these expressions, clearly this point to this point completely it's inside the liquid. So obviously you can see, if you do simplification, you can get rho Fg V submerged, and also this force is actually acting in the upward direction. Okay, so in the upward direction. Now what is the location of action of this particular point, for example? Okay, so what is the location of this point? If you take the first moments, if you define a coordinate system, for example, if you define any coordinate system here, if this is x and if this is z in general, so if you take by taking first moments, like again the case of hydrostatic forces, by taking first moments, we can see it's very easy, like we have done in case of hydrostatic plane surfaces. Similarly we can see here by taking first moments about this point. For example, you can see, let us suppose if this dfz is acting at this point, Okay, so the dfz is acting, or dfb, small buoyancy force, is acting at this point at a elevation, at a distance of x, for example. Then you can understand by taking first moments, you can see buoyancy acts to, fb acts to the centroid of the displaced fluid, the centroid of the displaced fluid actually. Okay, so it acts to the centroid of the displaced fluid. But one caution I would like to tell you, it's not like the fluid, the buoyancy always acts in the vertical direction. Okay, so do you feel that buoyancy always acts in the vertical direction? Buoyancy always acts in the vertical direction is what generally we study, but is it mandatory that buoyancy always acts in the vertical direction? Yes or no? Quick, everyone should type in the chat box. Come on, this is a nice point actually, which generally is asked in some of the interviews. Okay, so BRC exclusively. And is it mandatory that buoyancy always acts in the vertically upward direction? Don't know the reason. Yeah, actually it's no. Okay, the buoyancy will always act. Look, buoyancy always acts in the direction that is perpendicular to lines of constant pressure. Okay, so that's perpendicular to lines of constant pressure actually. Okay, so that's perpendicular to lines of constant pressure. If you do this same analysis in vectors, you can see this fb will be actually in this, like for example in this case. Okay, see here, in case of static fluid, what happens? Lines of constant pressure are horizontal. Yes or no? Lines of constant pressure are horizontal actually. Correct? We have seen whenever you have done the hydrostatic analysis, you found out in case of static fluids, your dou p by dou x and dou p by dou y are actually zeros. Yes or no? Dou p by dou x and dou p by dou y is equal to 0, right? Now you can see if this is the case, then the lines of constant pressure are actually horizontal. Yes or no? The lines of constant pressure are actually horizontal in case of static fluid. So if you take the lines of constant pressure as horizontal, that's why this is vertical direction. Okay, so this is the direction of buoyancy. Fb vertical. Let us suppose if we keep a body, for example. Okay, there is no body, no buoyancy obviously. So Fb vertical, because these lines of constant pressure, P1 equal to constant, P2 is P is equal to C1, pressure is equal to some value, pressure is equal to some other value, and so on. Pressure is equal to some value. So let us say these are horizontal lines. Okay, now let us suppose for example you have a tank. One more example, we'll see this in today's differential analysis. Okay, we'll see this in differential analysis. So you have a tank, for example. Okay, you have a tank. Then let us suppose if this tank is accelerating at an acceleration ax, for example. Okay, this tank is accelerating in the direction ax. Then let us suppose if the tank is initially at rest, the water surface in this tank is horizontal obviously. Okay, let us suppose if this tank is not moving, it's not accelerating, then in this case you have the water surface horizontal. Let us suppose if you pour water in tank, the water level becomes horizontal. But let us suppose if this tank is accelerating in a direction ax, then definitely this curved surface will actually tilt in this direction. This angle, for example, is theta. If this angle is also theta, then this is the free surface obviously. Okay, so this is the free surface in general, and the expression for this is tan theta is equal to ax by g, of course with a minus sign. Okay, how this is coming I'll show you in a moment maybe. Okay, so when I start differential analysis, I'll show you that normally this case is called rigid body motion, means the tank will the fluid in the tank will not get deformed, it just changes its orientation, that's it. Okay, the total the volume occupied with the fluid before and after will be same. Okay, so we call this as rigid body motions. Why it's called rigid body motions and all, again we will see when we talk about shear strain rates and all. So this is a rigid body motion actually. Okay, now if this is a rigid body motion, then you can see this tan theta is equal to minus ax by z. So this is ax. Then in that case, obviously the lines of constant pressure, if you check the lines of constant pressure, these lines of constant pressure are like this, correct? Because obviously PATM plus OGH, this H is equal to this H obviously. Okay, so this is how the lines of constant pressure are here. This is how we have the lines of constant pressure. Okay, so this is how we have the lines of constant pressure. Like for example, P is equal to C1, P is equal to C2, P is equal to C3 and all, P is equal to C4, all these things. Okay, now initially if you see, normally in a static tank, if you tie the balloon to some location, let us suppose if you tie, let us suppose you have a rod like this, for example, attach it to this pin. Okay, so let us suppose you have a rod like string attached to the pin, and let us suppose if you attach a balloon to this, for example. Okay, so you take a balloon and you attach here. For example, if you have a balloon here, initially the balloon will be like this, it is floating vertical, yes or no? If the tank is in static condition, the balloon will definitely float in the vertical direction, and this guy has to have a tension in this string. Now similarly, when this tank is accelerating, this balloon will take a new orientation, which is something like this, because this balloon is actually pushed in this particular direction. You can clearly understand, because buoyancy will act perpendicularly, and clearly you can also understand, let us suppose if we keep a balloon now here, definitely pressure at this point is higher than pressure at this point, yes or no? Because the fluid column on the left hand side is large as compared to the fluid column on the right hand side, yes or no? So when this fluid column is large on this left hand side, definitely the pressure acting at this point, let us suppose if you take balloon as a small spherical object, spherical surface for example, then the hydrostatic force acting on this left side is actually large as compared to hydrostatic force acting on the right side, and this will actually make the balloon to push towards the right, and it exactly pushes in such a direction that the orientation of the balloon means basically obviously the balloon will be in the direction which is perpendicular to this lines of constant pressure. So this is how the buoyancy acts in this case. Okay, clear logic that the pressure on the left hand side will be large as compared to the pressure acting on the right hand side. So definitely what happens, the balloon will actually tilt according to that particular direction. Okay, is this understandable to all of you? Clear to all of you? Okay, so whenever if someone asks you what is the direction of buoyancy, never say it's always upwards. Okay, basically it's always perpendicular to the lines of constant pressure because of this. Okay, because whenever lines of constant pressure are inclined, definitely the side with higher inclination will try to push the body in the other direction. Balloon left side hoga na? No, because you can clearly see because of this pressure it actually tilts in that direction. This is actually in the static case. Okay, so this is, you may get confused again, so this is actually static case, and this is obviously the accelerating case. Okay, it's a clear validity that the balloon moves right because the pressure at this point is high. Okay, so this high pressure will actually try to push it to the right actually, okay, not to the left. No, I'm not telling this is also static. In the initial case when tank is not moving, means if this is in static case, okay, if Ax is equal to 0, got it? When tank is not moving, if the tank is fixed with some Burma, it's very simple. Look, let us suppose you have a body, okay, you are pushing it in this direction with higher force and in this direction with lower force, then definitely this body will displace here. Okay, it moves towards right, that's it. Rigid tank means no boundaries is changed, and basically the volume of the fluid is also not changed. Okay, clear? Then we'll see one more small important things that which generally we see: floating of ice on water. Floating of ice on water. So sometimes these kind of little questions can be helpful. So floating of ice on water. So you can see again, you take a tank for example. Okay, you take a tank and let us suppose you have the water level up to this point. Okay, so you have the water level up to this point. Now let us suppose you have placed a small ice cube. Let us suppose you have taken a small ice cube actually which is floating like this. Okay, so it's an ice cube which is floating. Ice cube, and this is free surface of water. Okay, so let us suppose if you eliminate this line, for example. Fine. Okay, so this is what we have. Now clearly you can see this is floating and this is the free surface, and here we have water up to this particular point. Okay, so this is ice cube and water. But inside the fluid will change its shape, but volume not change. Yes, exactly. It actually changes its shape, but it's not even changing its shape. It's the orientation is actually changing. That's it. Okay, the fluid is not getting completely deformed or anything here. It's just getting adjusted, because liquids generally adjust with the shape of the container. So arbitrarily the container assumes a different shape because of this acceleration, and the fluid gets adjusted accordingly because of the pressure. Okay, it's like the fluid has just moved towards down. That's it. It did not get deformed or twisted at any point. Clear? Now, so let us see. In this case, let us suppose if this level is initially h. Now if ice cube melts, h will, what happens? Do you think what happens to h actually? H will increase or decrease, or something happens? What do you think here? H will increase or decrease? Let us suppose if this ice cube got melted, then what happens? H will increase or decrease? It remains same. Why? Ice is melting, no? So definitely we'll get some water. Level should increase. Yeah, it actually remains same. Okay, why it remains same? We'll see. H will remain same. So how this happens? Let us check for a while. Let us suppose if this is a cube, for example. So let us suppose the side of a cube is A, for example, and this is this height is actually x, for example. Okay, so let us say this height of submersion of the cube, this height of submersion is actually x. Okay, this is x. Now clearly in the initial case, weight of ice should be same as buoyancy on ice due to water. Correct? So this is due to water actually. Now what is weight of ice? Mass of ice into g is equal to buoyancy acting on ice is actually density of ice into, because you can see whenever you have calculated the buoyancy force, this calculation is depending on density of fluid, not on density of body. Okay, so therefore you should take the fluid density which is always supporting the fluid actually. Okay, now let us see density of ice into g into volume of submersion. So V submersion, which is actually equal to mass of ice into g, is equal to density of ice into, density of fluid actually, water. Okay, so water is actually lifting this, so density of water into g into volume submerged. Now let us suppose if this is a cube, at every point the cross section is actually a square. Yes or no? Because it's a cube, so cross section is a square, and these cross sections of a square are piled up to a distance of x. So a square into x is actually the volume which is submerged. Is this clear to all of you till this point? Everyone, Brahma, Sky, Ladani, Vanjit, AL, Rajput, Subhash, Mudit, Harsh, all of you. So please type in the chat box. Is this clear to all of you? Is this equation clear to all of you? Yes. Now let us simplify certain stuff. Z gets cancelled. So mass of ice can be written as density of ice. This can be written as density of ice into ice cube is of volume a cube. Okay, so density into volume gives mass obviously. Okay, so a square, you can cancel this a. So density of ice by density of water is actually x by a in actual case. Okay, so this is x by a, of course. Okay, so this is x by a. Now one important thing here is you can observe x is actually less than a. Okay, which means clearly density of ice will be definitely less than density of water, and ice floats on water, which you can generally see anywhere. Okay, if you take ice cube and if you put it in water, it actually floats. Okay, so that's why whenever you perform this calculation, since this ratio is less than 1, this ratio has to be less than 1. Yes, and we know geometrically that is less than 1 because this is x, this completely is a, x by a is less than 1 actually. Now let us see what happens. Now after melting, volume occupied by newly formed water. Why water is getting formed? Because ice is melting. Okay, so newly formed water actually is equal to mass of newly formed water divided by density of water, because it got converted to water phase now. Yes or no? Can I write this? Sir, a square वाला बता दीजिए. This a square, where is this? Is this a square x term? Okay, so you have a portion of a cube which is actually getting submerged inside the liquid. This height is x, this is a, and this is also a. Then this volume of this portion which is inside the fluid is a square into x. Okay. Yes, h remains same. That's what I'm explaining. Okay, so you can see here. H remains same, that's what I'm explaining. So see here, this newly formed water divided by density of water. Can I say this? Whatever the water you have formed by melting of this ice, that water will occupy a volume which is equal to the mass of the water formed divided by density of the water actually. Yes? Can I say this? Yes or no? Please type in the chat box. Everyone, can I write this? Whatever is the volume getting occupied by water, that's same as mass of this newly formed water divided with density of water actually. Okay, now you can see mass of newly formed water is nothing but mass of ice. Yes or no? Because whatever water is getting formed, that's getting formed because of melting of ice, and since mass conservation has to be valid, whatever is the mass of ice, the ice just changes its phase and it gets converted to water, so mass remains same in both the cases. Okay, so if you write this mass of ice, density of ice into a cube into, so density into volume is mass actually divided by density of water actually here. Okay, now density of ice into a cube by water, you can see density of ice by density of water can be written as x by a into a cube actually. So if you simplify this, then this becomes a square, so a square into x actually. Okay, so that means volume occupied by this newly formed water by melting of this complete ice cube, whatever the water is getting formed, that water is getting occupied in a volume which is equal to a square into x actually. Okay, so this is a square into x. What is this a square x? That's nothing but the initial volume which got submerged inside the water. Yes or no? So you have seen, after doing this analysis, this volume occupied is same as a square into x. So this a square into x is same as this volume which is submerged initially by the ice, which means whatever the water is getting generated because of this melting, complete water is getting adjusted in this volume of a square into x. Yes or no? Correct? Is this clear to all of you? If complete water is getting adjusted within that space, then what happens to the total h? Because of this complete melting of ice cube, the water is getting formed and that water is getting adjusted in this space exactly, which is a square x. Then obviously this h will not move. Okay, so h actually remains same. That's why this statement is correct. Okay, both लोगों को ऐसा लगता है कि अगर if this ice gets melted, then you know, because this equal amount of water gets formed, this h will increase. Okay, but that's not the case actually. Okay, I'll ask you one more thing, you can answer. Let us suppose in this block, let us suppose if I have a small air bubble. Okay, so let us suppose if I have small air bubble. Okay, so let us suppose if I have a small air bubble. So P ice a cube, sorry, ice a cube once again. I didn't get you. Density of ice by density of, sorry, what is this? I didn't get your question, Brahma, so please type once again. Okay, but my question to you is, let us suppose if I have a small air bubble here. Okay, then what happens? Do you think what happens to this water level? let us suppose if you have a small air bubble, okay, a very small air bubble, then what happens to this water level? Any idea? Let us suppose in the ice you have small air bubble, for example. Yeah, H will slightly decrease in that case, okay, because it will slightly decrease because you can see, because of this air bubble, the buoyancy force almost remains same, because this density of ice will be much high again compared to density of ice, so there won't be much impact in buoyancy. But in terms of volume, you can see when this ice gets melted, this air bubble will escape, okay, so that when this ice cube melts, there won't be enough amount of liquid to fill this a square x, so obviously some level will decrease, okay. Clear to all of you? Katia, Anjit, Kalyani, Midun, Ladani, Mudit, Mani, Brahma, Shivam, all of you. Sorry if I don't pronounce all your names, but I hope this is clear. Okay, so this is what you have. And similarly, if you have any heavy object here, like metal ball or something, then definitely water level will decrease in that case. Okay, we can again simply show using the same mathematical analysis, and we can show. Now, anyway, clear? I hope it's clear to all of you. Now, let us move forward to the next parts. Actually, stability of submerged bodies. Stability of submerged bodies. Okay. So before solving this, before going to the stability of submerged bodies, let us try to solve a question which was a nice question actually, which we kept yesterday. So let us solve this question so that we can get the answer. Wait, I'll try to do one thing. Hey, where is this? I have conducted, no? Okay, just a minute. See here. Oh, just a minute, it's not coming. Yeah, it's coming, fine. So let us see. Let us solve this question. I am putting it here and integer type. So I am also giving you some, like, yeah, 120 seconds. Okay, so please solve this and type the answer in the chat box. Mass of ice is equal to density of ice into a cube. Wallah. Once explain, sir. Mass is equal to density into volume. Okay, so the ice is actually in shape of a cube. So volume of a cube is a cube. If side is a, then volume is a cube. Density of ice into volume gives you mass. Okay, that's it. Come on. So please calculate this question. A block of wood of specific gravity 0.6. So this is our specific gravity 0.6 actually. Is floats in the fluid X. So this is actually a fluid X as shown in the figure, such that 75% of the volume is submerged in the fluid X. The gauge pressure of the air in the tank is dash pascals vacuum. Okay, so they are asking in terms of vacuum pressure, not the absolute. They want the vacuum pressure. Clearly, one thing is very fine. Obviously, if these two pressures are actually balancing, if this is atmosphere and if this is atmosphere, this pressure has to be less than atmosphere. Clear? So they are asking you vacuum pressure. That's it. Okay. So please solve this question and tell me the answer. Today we will slightly extend the class up to 9:45, okay, because it got delayed because of certain technical things. It started update, I don't know why it started. Generally, like every day I have started putting on the system 15 minutes before, but unexpected auto starts or updates are very dangerous, correct? Have you ever experienced this when making PPTs, when you are in some urgent commitment and if you are opening the laptop and suddenly it starts updating? Have you seen this anytime? Come on, the poll is running up. Yeah. Okay. So let us see solving this. First of all, one thing what we can do is wooden block of specific gravity 0.6 floats in fluid X as shown in the figure, such that 75% of its volume is submerged in the fluid X. Guys, try to understand something here. This block is some part in wood and some part in air. Can I say the buoyancy exerted by air is actually very less as compared to the buoyancy exerted by the fluid X? Yes or no? The reason for that is 3.14 kilopascals. I don't know, I have to solve. Okay, look here. So this is F buoyancy acting due to air on this block is very much less than F buoyancy acting on the fluid due to fluid X actually here, okay? Because even if there is a case, you can see weight of the block, if the block is floating, then definitely weight of the block should be equal to buoyancy force exerted due to air plus buoyancy force exerted due to the fluid X actually here, okay? Now physically if you see, definitely this will be low because this is clearly a liquid, okay? It's not a gas. How do you know it's not a gas? This is clearly a fluid. They told it's fluid, but I'll declare this fluid is actually a liquid. A liquid. Correct? Why? Because obviously if this block is floating, if wooden block is actually floating, the density, wooden block density is actually 600, okay? 600 kg per meter cube. If wooden block is floating at this interface, definitely this fluid density is more than 600. Yes or no? Otherwise this will not float here, it will sink. Correct? This fluid of X has minimum density of at least 600 or more than 600, otherwise it cannot support this wooden block here. Yes? Yes or no? All of you, please type in the chat box. Obviously it's yes. Second, I can confirm it's still liquid again, because if this is gas, you cannot use a open tube. Yes or no? If it is gas, this open tube will bypass the gas actually, okay? So because of these logics, we can say this is definitely liquid, and this is a liquid of density minimum of at least more than 600. So we don't know what is density right now, but we know that it has density more than 600, okay? Now why I have neglected buoyancy of air is actually, see, buoyancy, look, you can understand by the terms. You can, if I write, see, weight of the block is density of the block into volume, total volume of the block into gravity. So this is weight of the block. Now this guy is equal to buoyancy due to air, density of air into G into, look, 75% of the volume is submerged in fluid X, means remaining 25% is in air. So 0.25 or 25 by 100 times of volume of the block plus density of fluid X into G into 75 by 100 times of volume of the block actually, okay? So this is the equation what you can write for balancing. Now clearly, if this fluid is having at least density of more than 600, definitely density of air is maximum around 1.2 kg per meter cube of that range, but density of the fluid X is around something, this is, we know right now, we know that this is definitely more than 600 kg per meter cube. Kg per meter cube actually, okay? So this is more than 600 kg per meter cube. And secondly, compared to this term is large by 3 times. Yes or no? So this term and this term, if you compare, this is larger by 600 times and this is larger by 3 times almost, okay? Means compared to the first term, second term is larger by 1800 times actually, in the least case, okay? In the least case, if you assume this as 600, slightly 601, maybe something like that, this term is actually 1800 times larger than this term. So can I neglect this now? Yes or no? Can I neglect this in that case? That's why I have written this, because this term is actually around 1800 times more. This 1800 is the limiting case, okay, in order to just keep the wood there, but this is almost like 2000 or 2100 times more than this particular term. So we can neglect buoyancy due to air. Everything that we say, that definitely has a logic. We have to understand the physics behind it, okay? Now if you neglect this term, it's not like I like fluid X and I don't like air, I'm neglecting it, okay? You have certain logic why we are doing that. So density of block into V block into G is approximated as density of fluid X into G into 75 by 100 times this volume of the block actually. Now if you simplify this, volume of the block, G gets cancelled. So clearly density of the fluid X is equal to 4 by 3 times of density of the body, which is actually, density of the body is 600. If you take water as 1000, then specific gravity is 600. So 4 by 3 times of 600. So clearly this is 200. So around 800 kg per meter cube. 800 kg per meter cube. If you take this as 1.2 and all, I think the calculation will be maybe maximum 798, 797 of that order. Not even that much. Even it should be like close to 799 obviously, okay, because this is like 2100 times roughly, okay. Now this is 800 kg per meter cube. Now you got the fluid density. Let us see what happens. You got this fluid density rho x is around 800 kg per meter cube. Okay, so this is 800 kg per meter cube. Then if you can simplify this, let us see here. This location is 1 and this location is 2. Since this is a manometric tube, U-tube, the pressure has to be same at these 2 points. Okay, so P1 plus P1 should be same as P2. So if you write P1 is same as P2 here, P1 is equal to P2 from the concept of manometry. So what about P1 actually? So P1 is like it's atmosphere, PATM, because that's open to atmosphere. P air plus this column is of height 40 centimeters. So plus density of fluid X into Z into 0.4 obviously. So PATM minus P air, which is actually P air vacuum. P air vacuum is equal to density of fluid X 800 into G 9.81 into 0.4 obviously. Okay, so this is 0.4, so this is 320. So 320 times 9.81. So 320 times 9.81 actually. Oh sorry, just a minute. 320 times 9.81. So this gives you 3139.2. 3139.2 pascals actually. Okay, so this is 3139.2 pascals, and they are asking in pascals obviously. Okay, so nearest integer is 31. How much is it? 3139. That's it. 3139 pascals vacuum. Okay. So is this clear to all of you? Fine. So let us see. Some of you might have written correct in poll. So 313. What is the answer? 9. Okay. The poll is not getting displayed actually to you. You are not able to mark in poll. Please type in the chat box. Are you not able to mark it in the poll? Yes. Okay. Fine then. Yeah, it's okay. But I hope you all understood how we can do this. Okay. Whenever you're doing the questions, you should have certain physical logic behind the things going on. Okay. Fine. So, okay. I hope it's clear. Then let us go to the next concepts actually. Okay. So, yeah, you will actually solve one more question like this. Okay. So let us see. There is a cone like this. A cone floats in glycerin of specific gravity 1.26 as shown in the figure. If the radius of the cone is r is equal to 20, so this is actually 20 centimeters. It's a 20 centimeters cone actually. Okay. So if this is 20 centimeters, then the mass of the cone is dash kgs, round off to 2 decimals. Okay. So let us check clearly. Solution. Obviously, mass of cone or weight of the cone should be balanced with buoyancy. Weight of the cone should be balanced with buoyancy due to glycerin. So this can be written as mass of the cone into gravity is equal to density of glycerin into G into volume submerged. Now, how do you calculate this volume submerged? Actually, that's the main important thing. So this volume submerged is not directly given. Actually, you can see this particular part is getting submerged inside the glycerin actually. Okay. So how do you do this? Total cone volume minus, you can see volume submerged is volume of the cone minus volume above water surface or above the surface, above the glycerin surface, correct? Now what is this volume? You can see this height. If this completely is a cone, then definitely this is also a cone, yes or no? So this is also, you can see here, this is also a cone actually here in this case. Okay. Now in this cone the height is h 30 centimeters. Now what about this radius actually here? Obviously if you apply similar triangles, you can see good morning motor world. Yeah, so this height is 30 and this is r. You can see this small r by capital R is equal to small h by 30 plus 60, total 90 centimeters. Yes or no? Of course h also we are putting in centimeters, so I am not converting in units. So small r by capital R is equal to small h divided by total, which is 90 centimeters is the height. So small r is equal to capitalized 20 into small h 30 by 90 actually. So this radius is going to be 20 by 3 centimeters. Means the radius at this particular point is actually 20 by 3 centimeters. Okay. So therefore you can see volume of the cone is 1/3 pi r square h. So 0.2 square into this total h is 90 centimeters, which is 0.9. minus, which is the volume above floating, is 1/3 pi r square. So what is r square? 20 by 3. So 0.2 by 3 actually. So 0.2 by 3, 0.2 whole square by 9. Okay, so you can say this as 0.2 square by 9 actually, because 0.2 by 3 whole square into h, that's 0.3 again. So this is 0.3. So if you simplify this, then we can get the answer very easily. So let us see what we can get for this. Pi by 3 times of, simple calculation, the cone, only this little bit of geometry is the main thing. So pi by 3, 0.2 square into 0.9 into, okay, into 0.9 minus pi by 3, 0.2 square into 0.9 minus pi by 3, 0.2 square minus 0.3 by 9, 0.3 by 9 actually. Okay, so this is the volume which is getting submerged. How much is this? 0.036 is coming. Let us check this. Okay, so this volume submerged is actually coming out to be, let us punch some keys and let this calculation, 0.3 by 9, sorry, 0.3 divided by 9. Okay, now subtract this guy from 0.9 actually. Okay, so subtract this from 0.9, 0.866 into 0.2 square into 0.04 into pi divided by 3 actually. Okay, so divided by 3, 0.036 is what you are getting. 0.03629, yeah, 0.0363 roughly. So 0.0363. Okay, so this is the volume actually that you have. Okay, so 0.0363. So obviously you know gravity gets cancelled in both the terms. Then mass is equal to density of glicerin into this volume. So density of glicerin is 1.26 specific gravity. So 1260 is the density. So if you multiply this value with 1260, then 45.74 is the mass. 45.74 kgs is the mass of the cone actually, because gravity gets cancelled anyhow, and mass is equal to this submerged volume which you have calculated into density of glycerin actually. Okay, so are you all getting the same value? 45.74 kgs. So the mass of the cone which is floating is actually 45.74 kgs. The only thing is slightly we have to put geometry and we have to get the volume of this upper part. That's it. Okay, this question is easy as compared to this question actually. Okay, this slightly involves manometric and also certain understanding physics. Are you all liking the questions actually that we are solving? The hemispherical dome. In yesterday's class there is a curved gate where spring is pushing the gate actually. Okay, in manometers we have seen so many multi-tube manometers. We have understood why inverted tube manometers are again powerful. We have understood a lot of things actually. Okay, fine. So let us go to the next question. I mean the next concept actually here, stability of submerged bodies. Okay, now what is stability or stable equilibrium of submerged bodies actually? So you know equilibrium is basically in 3 types. Equilibrium of bodies is under 3 classes, like stable equilibrium, unstable equilibrium, and also neutral equilibrium. Neutral equilibrium. Like what is this stable, unstable and neutral is basically, see here. In case of stable, even if you give a small perturbation, okay, fine. So let us suppose even if you have a small, if you give small disturbance to the body, then definitely the body will again try to get back to its original position. So previous question of specific gravity given, from the density of fluid is 600, but when the wood is put it, the density is 800. So as also it is compressible fluid. Look, 0.6 is the density of the wood. Okay, it's not of the fluid X. Understood? I understand when you put the wood here, the fluid will slightly get down and get slightly lifted up in the left side. Okay, because some volume is obviously displaced by the block. Okay, it's not like the fluid is compressed and the left side limb is not at constant position. Understood? When you keep the block, because the block will occupy some volume which is initially occupied by fluid X, so that particular volume gets lifted up in the left limb and completely there is an equilibrium. Okay, if you take out the block, then definitely left limb fluid will also come down. Obviously, this should happen. Okay, now let us see in case of stable equilibriums. Let us suppose if there is a body at some particular state, even if you give some small perturbation or if you give some small disturbance to that particular body, then definitely the body has to come to its original position. Okay, so these are called stable equilibriums. Like for example, you can see whenever at any point in the phase change diagram. Okay, so let us suppose there is a phase change diagram for example, then at any particular point, if you remove some small amount of, if you supply some small amount of heat, and if the small amount of heat goes to atmosphere, then definitely it again comes back to its original position. Okay, in case of spring, for example, let us suppose if you give small elongation to a spring, and if you leave, after certain vibrations, again it comes back to the same initial position. So all these are the cases of stable equilibriums. Okay, like for example, let us suppose if I fix a spring like this, for example. Okay, if I if I hold one end of the spring, and if I slightly pull and if I leave, then what happens? After certain oscillations, the edge again comes back to its same original position. Okay, so these kind of situations are called stable equilibriums. Okay, like for example, you can see stable. So for example, if you write this things, stable equilibrium, body remains to its original configuration, or body set back to its original configuration, even after small perturbation, which is basically some disturbance. Okay, so let us suppose if there is some small disturbance. Like example, this is spring or stretching of the material within its elastic limit and all. Okay, so let us suppose, like for example, let us suppose if there is a beam, and if I pull it within the elastic limit, and if I remove the load, then what happens? The beam will again get back to its original position, but of course within the elastic limit. Okay, so yeah, ball in a concave curve, all these things. So basically the common examples you can see is stretching. Let us suppose if there is a beam like this, for example, if you fix it cantilever, let us say, and pulling or stretching it within elastic limits, Okay, if you remove the load, then definitely it will come back to its original configuration. Okay, so this is stretching within elastic limit, or maybe as one of you are telling, there is a concave, this thing, and if there is a ball here, if you give small disturbance, then after oscillating, this ball again comes back. So all these cases are of stable. Similarly, unstable is obviously when you give some small disturbance, the system will actually deviate from its position. Okay, like let us suppose, for example, you have this opposite. Okay, you have a convex curve. Then let us suppose in case of unstable equilibrium. So let us suppose, for example, if you have a convex curve like this, and if you keep a ball here, for example, okay, then what happens? If you give a small perturbation, this actually goes very deviating. Okay, so it goes very highly deviating actually here. Okay, any small disturbances, like for example at critical point in a vapor dome, there at any disturbance at that particular point will keep on changing the properties of the substance again. Okay, so in thermodynamics again we can see all these things, but this is actually unstable. Okay, this you can take it as an example. Similarly, neutral equilibrium, like for example, if you take a flat surface, for example, okay, let us suppose if there is a block, for example here. Okay, now what you're doing is, let us suppose you apply some small disturbance and you keep the block here, for example. Okay, let us suppose you slightly displace the block, then what happens? This block will not keep on deforming, will not keep on moving. At the same time, this block will also not keep coming back. This is a flat surface. Okay, it's not inclined. Then definitely what happens? The new configuration will become the permanent configuration of the body. So these are called neutral equilibriums. Okay, now if you design any body which is floating or maybe submerged, then can anyone tell me out of these three equilibriums which is actually suitable for us? Let us suppose you are designing something. Then if you are designing something, then clearly you can understand out of these three configurations, or out of these three types of equilibriums, let us call, for example, stable, unstable and neutral, then which case should be your design? Which case should be your design? Let us suppose it's stable, or maybe it's submerged, or maybe floating. It should be stable equilibrium, right? Even though there is certain small disturbance, the body should come back to its original configuration. Yes or no? Because it's not neutral. I'll tell you why it's not neutral. See here. Let us suppose if a ship is moving, for example, ship is floating body in general. So, or let us suppose some submarine is moving, which is actually submerged inside the ocean bed. So now you can see whenever the ship is actually moving, let us suppose some wave has come and hit the ship, for example, because of which the ship has slightly tilted like this. Now, when the wave has hit the ship, if the ship is slightly tilted, you want the ship to come back, yes or no? It's not like you keep on traveling the rest of your journey with an inclined ship like this, okay? Or it's not like when some small wave come and hit, it keeps on continuously tilting and finally it should sink. These two things should not happen. So every design what you should make should be within the should be within this particular stable equilibrium case, except few processes like in case of metal forming, in case of rolling, forging and all. There you again keep the body in some localizedly stable because of force analysis and all, but finally you will continuously deform the materials, okay? But whereas in case of tests and all, generally we do this with stable equilibrium, okay, to get the better understandings. So stable equilibrium, clear? Now what should happen with the yeah, obviously ship should come back, no, after hitting the wave, okay? It should not stay like that, clear? Now let us see in case of submerged bodies. In case of submerged bodies, what you can do is, let me help you with the help of an example. Let us assume there is a body, for example, like this. Okay, so this is what you have. For example, this is the body which is submerged. Now let us suppose this is the axis of this body, for example here, okay? So this is the axis of this body. Now let us suppose you want to tilt this body, for example, okay? So let us suppose this is the center of gravity, and let us suppose center of buoyancy is here, for example, okay? Why this is, I am writing this point extensively above this G, you will understand within some time. Now let us suppose I have given small disturbance to this body, okay? If I give small disturbance to this body, remembering party at night, oh, fine, see here, yeah, gas cylinder, oh, looks like a gas cylinder, maybe. Which looks like a gas cylinder, this diagram or me? This diagram, na? Not me, I am thin, okay? Fine. So let us see, this is gravity and this is FB actually. Now if this is FB, see here what happens. Whenever you try to rotate this slightly, whenever you try to give small disturbance like this, obviously the shape of this body, or basically the orientation of this body gets changed, yes or no? When you apply certain slight load, this configuration will assume a shape like this. So you can see this is how it happens, okay? Why I have done only gas cylinder, I will tell you, okay? Matlab this shape, okay? Now tell me one thing, you are trying to disturb this body, so this is the destroying couple, or external couple, let us say, external couple, external moment, we can say, for example, you are trying to rotate this body, okay? Now let us suppose if there is a submarine and some wave has come, and in the deep ocean, of course in the deep ocean the velocity of the wave is actually very small, but let us suppose because of some fluctuation, some pressure wave or something, it got tilted like this. Then whenever this is in this particular configuration, clearly the lines of constant pressure are still horizontal, so definitely buoyancy keeps acting in this direction, F buoyancy, this is center of buoyancy B, for example. So this is buoyancy force and this is weight force in general, okay? And if this body has to be here, definitely these two should balance each other, okay? Weight will be always equal to buoyancy force, okay? So weight is always equal to buoyancy force. Now if this is FB and G is actually somewhere here, weight, so G and B. Now clearly one thing you can understand is, if you draw a vertical line, then these two will have certain separation, yes or no? These two will have certain separation, which is E actually in this case, okay? So this is small separation, this is E. Now try to understand one thing, if this couple is trying to rotate this body, which is actually clockwise in direction, because of these two forces are equal, obviously weight has to balance the buoyancy, otherwise body will sink, okay? So at this point weight and buoyancy both are balanced each other. Now if these two forces are equal, then definitely there is a couple acting on this body. Can anyone tell me, this is weight acting downwards and if this is buoyancy acting upwards, can anyone tell me what is the direction of this moment? Clockwise or anti-clockwise? Can anyone tell me what is the direction of the moment that's acting here? Anti-clockwise, okay? It is anti-clockwise, yes? So this is a anti-clockwise moment, obviously. Now the external disturbance which came into the picture is trying to create a clockwise moment, but whenever this G is lying below B, then definitely what's happening, this couple is getting adjusted in this direction such that it again want to keep the body back in the original position, yes or no? So you can clearly understand this couple generated is trying to rotate this body again in the anti-clockwise, and this will try to restore the original configuration of the body. So that's why first stable equilibriums, this G, center of gravity, should be below the center of buoyancy actually. Clear? Yes, it means stable condition. Okay, so it is stable condition. So obviously this G should lie below B. You may feel, what happens if I rotate the left? Okay, because some of you may feel that because I have rotated this right side, that's why it is creating anti-clockwise. What happens if I do it left? Okay, you can understand clearly. Let us suppose if I do it left, say like this, for example, and let us suppose if this is the axis and if this is the disturbing couple, if this is weight G here, and if this is buoyancy force FB here, means buoyancy G is actually below this B. So in that case also you can see this couple is actually clockwise. Okay, so you can see these two will actually generate a clockwise couple. So this couple which is generated here is actually a clockwise couple. So if this disturbance is trying to rotate this anti-clockwise, then definitely this will have a counterclockwise effect which tries to keep the body in the same configuration. If disturbance is in anti-clockwise direction, then FB also shifted. No, FB will not shift. Okay, this is the case. Understood? If I understood. Some of you may think that what if the disturbance is anti-clockwise? If the disturbance is anti-clockwise, as long as this G is below this B, then definitely this W will actually create a clockwise couple and it will try to restore this configuration. Okay, so basically for stability of submerged bodies, submerged bodies, definitely, for stability of submerged bodies, center of gravity lies below center of buoyancy, below the center of buoyancy actually. Okay, so it should lie below the center of buoyancy. Okay, so this should lie below the center of buoyancy. If you, for example, I'll ask you the same question. Let us suppose if I shift these 2 points. For example, instead of having this, if I have G here and B here, for example, so buoyancy is in this direction, weight is in this direction, then clearly you can see this force is upward, this is downward, so this creates anti-clockwise, this disturbance is also anti-clockwise, so definitely the body will be in unstable equilibrium. Okay, understood? Let us suppose if I interchange these two, for example, you can understand this actually produces anti-clockwise movement which is in the same direction of this disturbance, external effect. Okay, then definitely body will keep tilting and it's an unstable equilibrium. Okay, so this is a condition. So therefore if you summarize, we can see G below B stable, this is only for submerged. Okay, stable equilibrium. Then G above B will be unstable equilibrium, and G coincides with B, it's in neutral. Obviously G coincides with B, because obviously if these two are coinciding at the same point, there won't be any moment that gets generated, so this is neutral. If you tilt the body externally, the body remains there. There won't be any disturbing or restoring couples actually at this point. Okay, have you ever seen a submarine at any point? Have you ever went into submarines at any museum, or in Vizag we have one? Okay, INS Kalyani. So did anyone of you see any submarine actually? Photos? हाँ, फोटोज में देखा था ना, ठीक है, मैं एक फोटो दिखाता हूं तब. सबमरीन ब्लूप्रिंट. Images, if you see, yeah, generally this is a good image, maybe. Normally if it's, yes, this is actually a submarine. Okay, so you can see the submarine blueprint. Can anyone see one thing here? If you observe carefully, all the engines and all are at the bottom. Can you see this? Yeah, in Vizag you might have seen, because in Vizag we have the one expo of a submarine. But right now, can anyone see this? This is the actual blueprint of one of the companies. Maybe I don't know who is this. Dean's time license details and all. Okay, fine. Let's not go into much details. But have you ever seen? If you see, the majority of the ballast water, you can see the simulation also, the majority of the ballast water, engines, all these things are here. You can say roughly the middle part or the top part of the submarine is roughly empty. Correct? It's like a hull. Means basically used for the people movement and all. Okay. Then can you see, understand one thing? If you want to keep gravity below center of buoyancy, obviously center of buoyancy will be the geometric centroid. Yes or no? When submarine is completely submerged inside, obviously you will dip the submarine in the sea. So whenever you dip the submarine, the geometrical center will be somewhere at the midline depending upon the volume and all. But in order to have stable equilibrium, your center of gravity should be below your center of buoyancy. Okay. If your center of gravity has to be below your center of buoyancy, definitely the body has to be bottom heavy. Yes or no? Means if you see the body should be heavy at its bottom. Yes or no? Obviously only then this center of gravity will like this. I'm erasing. Okay. So anyway, you might have understood. So for this to happen, body should be bottom heavy for this to happen. Yes or no? Because centroid or center of gravity should be heavy bottom body, means is in stable condition. Yes. Okay. So if you want to make a body heavy, definitely you should keep all the heavyweight components at the bottom of the body. Okay. So that's why in a submarine, if you see, if you might have people who is in Vizag or at some other locations, if you enter a submarine, you can see all the engine compartments, all the engine rooms or the heavy water tanks and all, they'll be at the bottom. You might have seen this. Okay. This is the reason. Okay. Is this clear to all of you? This is because of, this is happening because of this. Okay. Shall I ask you one doubt? You might have seen ships sometimes. Okay. In ship, engine rooms and all, the captain controlling or the engine rooms, all these will be on the top or bottom. So neutral equilibrium is basically both this weight and center of buoyancy will, this gravity, center of gravity and center of buoyancy will actually coincide. Have you seen a ship anytime? In case of ships, the engine will be at the bottom or at the top? At the top. Correct? Via controlling tower, obviously at the top. Correct? At the top via controlling tower. Then why this condition is not holding? Come on, quick. Why this condition is not holding then? Look, I'll tell you. These conditions are first submerged or floating? Submerged. Okay. You want to float the ship or you want to submerge the ship? You want to float it, right? Obviously you should not submerge. If you submerge, then obviously you cannot do the things. So how sea visible if this is at bottom? Which is at bottom? Inside the sea, it's not like you see the windows and all. You actually have the telemetry, okay, to see. You want to submerge the ship, okay? You don't want to you want to float the ship, okay? You don't want to submerge the ship, okay? So the physics is something different there, okay? Not having the engine room at the bottom of the ship. Clear? We'll see again, okay? So anyway, this is the story. Now let us see certain things. Stability of floating bodies, okay? Stability of floating bodies. So stability of floating bodies. Okay. So in case of floating bodies, just this concept of centroid and buoyancy cannot actually make you understand the things. Okay. So there are certain different physics which actually governs the stability. Okay. It's not just like your maybe center of gravity or buoyancy alone can decide your things. Now let us see in case of stability of floating bodies. Let us suppose if you have this body, for example, again if I take this bottle kind of thing, for example. Now let us understand one thing. Again, as per your stability criteria, let us suppose if you keep G here and center of buoyancy here, for example. Okay. So this is buoyancy force and this is weight, clearly. So weight and buoyancy, this is FB. Then if this is weight and if this is FB, then try to understand something. Let us suppose if I give a anti-clock tilt, for example. Okay. As per your condition of submerged bodies, this should be in equilibrium. But right now, let us suppose this is floating. Okay. So this is actually floating body. Now, whenever this is floating, this is, let us suppose some wave has come and hit the ship, then let us see what's happening here. This is the disturbance. Then it is actually the case of floating, and this weight has to still balance the buoyancy, otherwise this will sink. So weight has to balance the buoyancy. Okay. Now try to understand one thing here. Let us suppose if this is W, for example, this W will act like this, and this buoyancy will act like this again here, like in this case. Now try to understand one thing. Whenever the ship is rotating, this is the axis or point of rotation for this body, or in effective you can say this is about this axis. We will actually see, for example, here. So this is B, okay, so this is a G obviously. Can anyone tell me this B, whenever this body is floating, this B, after tilting, this B still stay on the axis or will it get diverted slightly? Can anyone tell me this? My question is, this object, if this is G here, this is G, this remains on the axis because it's a complete body. Coming to the center of buoyancy, this center of buoyancy will actually still remain on this axis or will it get tilted? Diverted, correct? Because submerged volume is, look, it gets diverted because the reason for this is volume submerged will remain same, total will remain same obviously, okay. So volume submerged will actually remain same. Now if this volume submerged will remain same, then what you can do is, you can see this center of buoyancy will actually shift slightly like this, okay. So this is center of buoyancy, it will actually slightly shift, okay. It gets tilted or it gets diverted because initially if this is the water level, it is exactly at the center, but now on the left side some part of the liquid is going out of the, some part of the body is going out of the liquid. On the right side some part is coming excessively, so definitely the right side has higher amount of volume inside the fluid, so this buoyancy will actually shift, okay. So this buoyancy will actually shift and this force will be in this particular direction, FB actually here, okay. So this is FB. In this case it appears like it produces an anti-clockwise moment, but again you can understand one thing. This E, let us suppose if this is E, the moment which is generating is equal to weight, for example, into this eccentricity, yes or no? This E is actually playing a role. Here if you see, in this case, this distance between these two is actually fixed because these 2 points are not going to get shifted. So this E is always locked. But here what's happening in this case, since this B can move according to the amount of tilting that's happening, yes or no? Sometimes B can be just getting displaced by slight amount, sometimes B can go by more amount, means the moment which actually creates this rotation is not fixed actually, okay. So this depends on this E. Clear? So did you understand this? Did you understand this actually? Yes or no? Is this clear? The moment which tries to restore will actually depend upon this eccentricity or the amount by which B actually shifts, okay. See here, this point will actually get tilted, and the moment if you wait, for example, if the separation between these two is E, it's not guarantee always that this point will shifted only by this much amount, okay. So depending on the tilting, it can shift sometimes here or it can be slightly close here, so it actually creates certain ambiguity, okay. So W into E. So only this particular concept is not sufficient to know about the stability of these bodies, so therefore we go for this point which is called M, and this M is called meta center, okay. So this is called meta center, and obviously this meta center is actually point of intersection of line of action of buoyancy with the axis of the body, the axis of the body actually. Okay, so with the axis of the body. In this case, you may observe that clearly B is above G and this produces anti-clockwise movement. Let me draw you one more configuration, it will give you much clarity. Okay, so now let us suppose, for example, if I take a configuration where like this, if you take a configuration like this, for example, and here this is G is somewhere here, and this buoyancy which is initially here B, but now because of this tilting, let us suppose this B got shifted to some location here, B dash, for example. Okay, so in which cases buoyancy forces will be along its axis. If the body is in vertical condition, that's it. In case of static fluid, if the body is in vertical condition, then definitely buoyancy will also be along the axis. Okay, now in this case you can see, because of this tilting, this buoyancy, let us suppose this is the free water surface level, for example, this is the free surface, then because of this tilting, if buoyancy gets shifted from here to here, then you can understand this buoyancy FB, okay, and this buoyancy FB actually, this is buoyancy, and clearly this is weight, so this is weight actually here. Okay, so this is weight, so this is weight and this is buoyancy, and this is producing an anti-clock couple. Okay, but let us suppose instead of this B going to this point, let us suppose it got landed up here, for example. Okay, so try to understand, instead of this B getting shifted to here, let us suppose it got just shifted slightly by small amount, then in that case buoyancy will be acting in this direction and these two will try to further deform the body. Means you can understand one thing, in deciding the stability of this body, the shifting of B is actually playing a very important role. Yes or no? Because if this B moves on this side, then definitely what happens, this total moment due to this weight and buoyancy is creating an anti-clockwise movement. But in this case what's happening, this buoyancy and gravity are creating a clockwise movement and it's further tilting the body actually. Okay, so therefore you can understand, since the stability is dependent on this B, in actual case what's happening, try to understand, if this is the vertical line W, as long as the shifting of the B is to the left side of G, the body is in unstable equilibrium, and as long as the body or the center of buoyancy moves to the right side of this weight line, then definitely it produces anti-clockwise movement. Saying the statement like movement of B is same as, try to understand one thing, if this is the point B, for example, means if buoyancy is lying to the left of weight, definitely the line of action of buoyancy meets this axis somewhere below G. Yes or no? Means M is somewhere here. But if this point B shifts to the right side of this weight, then definitely this line will be at somewhere here. Yes or no? Means my point is to tell you, if the shifting of B is to the left of the weight, then definitely the point of intersection with the axis, which means the meta center, lies below G, and if the center of buoyancy shifts to the right side of this weight, then this meta center will be lying above G actually. Okay, so and you know, shifting of B to the right side of weight is the case of stable equilibrium, means for stable equilibriums this meta center should lie above G actually. Can I say this? In this case you can see clearly shifting of B decides stability as long as B is within this vertical line of weight. This is still trying to further deform the rotate the body. Okay, but whenever B is just crossing this line, it's starting to create a anti-clock moment. That means this B shifting to the right side of this weight will actually create a stable or some restoring moment. Saying this point is same as lying this meta center, this point of intersection, if it's below G it's unstable, and if it's above G it is stable actually. Okay, so M is the meta center for which I have given the definition. So first, stability of floating bodies, first stability, G lies below M. Okay, and for unstable equilibrium, G lies above M, which is like this. In this case you have seen. For neutral, obviously both of them coincide because no moment should be acting. So for neutral equilibrium, G coincides with M. Okay, so G coincides with M actually in this case. Clear? Is this points clear to all of you? Why these things are happening? Why meta center should be above? Why meta center should be low for unstable? Is this points clear to all of you? Projection of FB gives the location of M. Yes, basically, if this is FB, if this is the line of action of this force, the point of intersection of line of action with its axis is called meta center. Okay. So in floating bodies, if G greater than B, but both G and B is less than M, then what happens? Unstable or stable? If both B and G are less than M, then definitely it's unstable. Okay. Basically, it doesn't depend upon the sole position of B and G. It depends on the position of M and G because of the explanation what I have given so far. Okay. Is this everything clear to all of you conceptually? Because you have to understand all these points. Okay. Now, you can understand few things clearly. This point meta center physically is nothing but instantaneous center of rotation. Center of rotation actually. Okay, so this is instantaneous center of rotation actually. Means whenever you take the rotation of this body is assumed to rotate about this particular point, and clearly this body oscillates about this point M because this buoyancy force is passing through this, and when this is the axis, this weight decides the orientation of the rotation actually. Okay, so we can see this M meta center is called instantaneous center of rotation actually. Okay, so this is instantaneous center of rotation, and GM is called metacentric height. Okay, so this is called metacentric height actually here. Now in this case of metacentric height, try to understand if the distance between these if the distance between these two lines is large. Let us suppose if this is E for example, if E is large, that means this restoring couple is getting increased. Yes or no? Means if you want to tell one thing, as long as the separation between these two increases, it's highly possible that the body becomes in stable equilibrium. Yes or no? Means as this E increases, this stability of the body increases. Can I say this? The stable equilibrium of the body increases. Can I say that? Can I say that? Yes or no? Everyone, come on, type in the chat box. Can I say this? As this separation between these two increases, there is high chance that the stability of the body increases. Stable equilibrium of the body increases. Now, if E is increasing, that means, can I say, let us suppose if I shift this line of buoyancy from here to slightly right, this point will shift slightly top. Correct? Let us suppose if I am shifting this line to the right, then this point will shift to the top, because instead of having this intersection here, maybe this line will intersect it somewhere here. But this G will remain constant actually. Okay, so G remains constant. That means, can I say the separation between G and M, if this is high, then definitely stability is high. If the separation between GM is low, then definitely the stability is slightly low actually. Okay, means for stable equilibrium, stability is proportional to metacentric height. Metacentric height, which is GM actually. Okay, so normally you keep very high values of GM in actual case. Okay, if it's a ships which are actually traveling a lot of things and all. So in what situation FB displays more, the tilting has to be more. That's it. Okay, look, this tilting has to be more. Then this FB display, this point of buoyancy, actually center of buoyancy displaces large. Okay, look guys, look, simple analogy I'll give you. See, very simple analogy. See here, let us suppose there is a ship floating. Okay, now if there is actually a ship which is floating, then in that case, practically let us suppose if a small wave came and hit the ship. Okay, so let us suppose, I'll show you in this view, it's better. So let us suppose if a ship is moving in this direction, then in that case, let us suppose some small wave has come and hit the ship, then definitely ship gets actually tilted slightly. Yes or no? When ship get tilted slightly, what happens? This B displaces slightly, but of course we'll design the ship such that at any given point of time, this GM will adjust the configuration such that this G lies slightly to the left actually. Okay, so if you design the ship such that this GM is always positive, it's in stable equilibrium because you don't want to collapse the ship. Now when this displaces slightly, this E will be small, and for a small disturbance of the ship, the destroying couple will also be small. Now let us suppose if the heavy wave, a high wave came and hit the ship, then when the ship gets tilted by large amount, then definitely the destroying couple has also to be large. Okay, and obviously this E value depends upon the tilting, and the balancing is done by itself once you design the ship for GM greater than 0. Okay, rolling and pitching, we will see rolling action and pitching action of the ship. Okay, fine. Is this clear to all of you? So this meta center actually decides the case, and this GM actually talks about the stability in these bodies. Now, how do we calculate this GM? That's the most important thing. Okay, right now I'm not doing the derivation, okay, because it's fast actually. So GM can be written as, look, you have all the 3 points like this, and let us suppose this is the initial configuration of the body, for example. So if this is the initial configuration, so let us say if this angle is theta, this angle is also theta, then you have maybe B here, G here, maybe M here, obviously. Okay, then we can see GM can be written as BM minus BG actually. Okay, so BG, where this BM is called metacentric radius, and this is called metacentric height, actually. Now how do we calculate this BM is actually, look, BG you can easily calculate because you know how much amount of, normally for example, even if for complicated shapes you can calculate using integration and all, but right now you can see, let us suppose if you have simple shapes like cube floating on water, cylinder floating on water, triangular prism floating on water, let us suppose if you have these things, then BG can be easily calculated, yes or no? Because you know, like for example, let us suppose if I take a cube, okay, I'll tell you with the help of a cuboid, for example. Okay, let us suppose if I have a cuboid, and for example, let us suppose if this is the water line. Okay, so this is the water line. Then clearly one thing can happen, G is somewhere here, maybe B is somewhere here, because centroid of this part is maybe somewhere here. Let us suppose this is B, this is G, for example. If this total length of the cylinder is known, you can calculate half of this length. Okay, so this is L by 2. If this is total length L, and let us suppose if X is the amount of submersion, then clearly you know this center of buoyancy is actually at a distance of X by 2. So L by 2 minus X by 2 gives BG, obviously. Okay, so simple geometry, using simple geometry you can calculate what is BG. But how to calculate BM? That's the important thing. So BM is actually equal to IYY by volume submerged. Okay, right now I'm not showing this derivation. If you want, I'll upload in the Telegram channel. Okay, so but this is actually this metacentric radius actually. What is this IYY? Many students they commit mistake when they are calculating or substituting this moment of inertia. Okay, because everything is very simple, but this moment of inertia when they are substituting, they'll make mistakes. What is this YY axis actually? Okay, so if you see, if you cut this water line, then you will see in the top view a cross section, yes or no? So obviously, okay, let me draw here. For example, if you cut this cross section, then you can actually see a cross section like this. Okay, so let us suppose you have, for example, here in this case it's a rectangular cross section. Then this is the axis about which you have to take the moment of inertia. This is YY, means in other words, this is the top view, means in the front view when you see, if you cut this body at this water line, obviously you will be seeing a cross section. So the moment of inertia about this cross section, which is perpendicular to the plane of the board. Okay, if you see in the top view, obviously you will see a line like this. So you should cut at the water line, and if you cut at the water line, then this axis about which the the moment of inertia has to be calculated. Many times students write mistake here. The reason is, even in some books I have seen, sadly, that people say moment of inertia about this axis, means you see the object from the top view, then definitely whatever is the point here, so moment of inertia about this point. That's actually not very much clear, because I'll tell you, whenever you have bodies like cuboid, cube, things like that, this cross section on the top and this cross section on the water line is same, obviously. Okay, because you can see this cross section. Let us suppose if you see from the top, whatever is the rectangle you are seeing here, if you cut this body and if you see the water line cross section, you will again see the rectangle, the same rectangle. But let us suppose if I have some bodies like cone and all, then in case of cones and all, definitely the cross section here and the cross section here, even though they are at same shape, but they are not at same size. Yes or no? Clear? Is this clear to all of you? Did you understand? It's not mandatory always like the cross section here and the cross section here are same. Like in case of cone, they are not equal. Let us suppose if you take a cone, a floating cone. See, let us suppose if this is your water surface, and if you have, for example, a floating cone, okay, maybe something like this, let us say, okay. So let us suppose you have a floating cone like this, okay. Now, whenever you have a floating cone, then you should always take the cross section at this point, okay. You should always take the cross section at this point and not from this point, okay. So you should always take the cross section at the water line. And obviously if you see the cross section, we have a circle like this, you have a circle like this, okay. So you have a circle like this, small circle, then clearly this is the axis about which you have to take the moment of inertia. This is YY, okay, because clearly here the cross section and here the cross section are, they both are in circular shape, but the size is actually different, okay. Because when you are doing this derivation, you will see this cross section or this moment of inertia, when you are writing integral y square dA, all these things, you will see the area for which you are writing moment of inertia is this waterline area, but not this top area, okay. So at the waterline, this perpendicular axis is what the axis you have to take for the moment of inertia in this case, okay. Now I would like to ask or tell one particular important small thing. Stability of ships, if you see, stability of ships, okay. So stability of ships actually here, I'm not doing derivation again. I think this document was already uploaded in the Telegram group with the name stability of ships. Around 2-3 months back I have uploaded it to someone, okay. So you can see stability of ships actually. In case of stability of ships, normally if you see the shape of a ship, it's like this, a very long, normally sometimes it will be like some 200 meters also, very large ships. This is how a ship appears to you if you see from the top view, correct? Now whenever you see this from the top view, these questions are very important in L&T interviews and all, okay. Normally they ask you. Fine. So see here, let us suppose if I call this axis XX and axis YY, for example, okay. So this is axis XX and also axis YY. Now whenever you see rotation about XX or oscillations about XS, you can see oscillations about XX is called pitching, obviously, and this oscillations about YY is called oscillations about YY is called rolling actually. So oscillations about YY. So like for example, this is my length of the ship. Khaliwa L&T ka interview. Acha. Fine, okay. So let us suppose if this is the ship, for example, you know, this motion is called rolling, where this ship actually oscillates about the long axis, okay. So about YY, this is called rolling, and obviously you can see pitching, okay. Based on your knowledge, you might have seen some YouTube videos or in some movies and all, generally you might have seen. Can anyone tell me, out of this pitching and rolling, which is dangerous actually? Which is dangerous? Out of this pitching and rolling, which is dangerous actually? Pitching or rolling is dangerous? Rolling, YY axis. You see, any mechanical failure of the ship, because of mechanical balancing failure, the ship always fail by rolling actually, okay. The ship generally fails by rolling, but not pitching. For example, I'll tell you, in YouTube and all, whenever you see some videos of ship motion and all, not the pleasant cruise ship, but normally a ship with cargo and all, if you see, Normally in case of cyclones and all, what happens? The ship pitches very high. Yes or no? You might have seen. Let us suppose if this is my length of the ship actually raises by very large amount and falls. Okay, so pitching is very, pitching can happen at very high amplitudes also, but the ship will still be in stable position. But let us suppose if you see rolling is highly dangerous, and all the mechanical balance failures of ships are due to rolling. Okay, the reason for that is, look, I'll tell you, GM is depending on BM clearly. If you see, for example, if you take the moment of inertia about this body, okay, so for example, if this is Y, this is large. Similarly here, if you see, this is generally small, and clearly the length of the ship is many times large as compared to its width. If you, for example, you take Y square dA and X square dA, of course, you may tell me that what happens if I take a cross section somewhere here, then it will be very near as compared to this. Or maybe if I take a small cross section, maybe somewhere here, then this is very small, but this is very large. Okay, you may argue, but still compared to this width, the length will be more. So selection of this type of elements will be less as compared to selection of this type of elements in this diagram. Yes or no? Means clearly majority of the area lies away from this axis, and in general, if you take on an average, this value will be very large as compared to X square dA. Yes or no? Because this length is very large. In an average, if you take at some random location, not very close to X axis and also not very close to Y axis, if you take some region, definitely this is what you have. Yes or no? And if you perform this integration, then clearly integration of Y square dA is nothing but moment of inertia about this axis. Ixx is very much greater than Iyy in general. Okay, so that means if you put this moment of inertia in these calculations, and if you look at the metacentric height, and if you keep stability of the ships is very much high in case of about this axis xx as compared to stability with respect to axis yy. Okay, so stability in the direction xx is actually very much greater than stability with respect to the fluctuations about yy actually. Okay, is this clear to all of you? Is this clear to all of you? Yes? And generally, whenever, if you see ship failures, I'd like to, because this is a smart board, we can take some advantage. So ship failures, if you see images, you can clearly see not the breaking of the ship, but you can see all these ships. You can see basically here, these are completely mechanical failure, metallurgical failures. But if you see all the ships, then this is rolling failure, majority of rolling failures, except whenever it is some material failure. Unless it is material or metallurgic failure, like the case of Titanic, the mechanical failures will be always due to rolling. You see one side of the ship gets into water like this. Okay, the reason for this is actually this. The ship is highly stable about the pitching axis, but very low stable in general when compared to the rolling axis. Okay, whenever it's metallurgical or material failures or direct impact failures, like for example in the case of Titanic and all, what happens? You may have it out. Normally ship is made of steel. Okay, and whenever you may have it out, whenever it hits an iceberg, being a ductile material, normally steel is ductile, you know. So whenever you create certain type of fracture to ductile material, what happens? It elongates a large before getting fractured. Okay, it doesn't get broken like a brittle, like a chalk piece. Okay, but why in case of Titanic this failure is actually brittle failure? Have you ever examined how actually Titanic failed? I know majority of you might have watched the movie, but do any one of you analyzed or thought in a mechanical point of view why the breaking happened all of a sudden, like brittle failure? Have anyone found some interest in this? It reached equicoefficient temperature. Fantastic. Yes, due to low temperature. Correct. Normally we have something called ductile to brittle transition. So if you keep any body at low temperatures, for example for a consistent period of time, and if you create impact, the fracture will be like a brittle fracture. Okay, so basically it's called the equicoefficient temperature. So at this equicoefficient temperature, what happens? The nature of the material changes from ductile to brittle, obviously, and so definitely it breaks all of a sudden. That's what it happened with Titanic actually. So in these cases, the metallurgy or material failures may be in any direction. It can be about this axis or this axis at any direction. But mechanical balance failure will always be about the axis with low moment of inertia, which is actually the rolling, obviously. Okay, moment of inertia actually is a physical significance of inertia to rotation. Okay, whenever you are talking about moment of inertia, physically moment of inertia means the resistance of a body for its rotation. Okay, it is measured by its moment of inertia. The name itself tells you moment of inertia. So if the inertia is low, then definitely the moment generated by it is also low. So which means whenever you try to disturb any body, it easily accepts you. Okay, it just rotates. But if the moment of inertia is high, the name, see, when I'm telling moment of inertia means the moment which is generated by this inertia is actually less. That means any external agent can easily disturb the body. So that's why when moment of inertia is least about this axis yy, then clearly any wave coming and hitting, or basically some other cyclones or whatever the failures that happen, or because of mass shiftings in this. So if you see, the ship can easily get failed about rolling axis actually. Clear? So is this understandable to all of you? Okay, but one look, engineering is all about what you learn in class is exactly what you see in outside. Okay, or basically what you see out is what you read in books. If you have a strong connection between these two, your knowledge levels will be damn amazing. Clear? So let's get into the things. Only one disadvantage with this is, right now I'm not doing again the analysis, but you can see time period of oscillation in floating bodies. We'll upload the document in the Telegram. It's already there in the Telegram group actually. So we'll see that. Velocity depends on that. While cyclone, speed is reduced to 5 knots from 30 to 34 knots. Yes, generally velocity is also reduced because if normally it's like impact of two high moving bodies. That's it. Okay, wave and ship both are moving at high velocities, then definitely the effect will be large. So you cannot control the wave velocity. So better you come down the ship velocity. Okay, that's what we do. Okay, now let us see time period of oscillation of floating bodies. Time period of oscillation of floating bodies is inversely proportional to square root of gm actually. Okay, this we will you'll get this after doing a bit of differential analysis equations and all. You will end up with a simple harmonic motion theta double dot plus w gm by I theta is equal to 0. Such kind of equations is what you will generate. Right now I'm not deriving these equations, but again you can see that in the Telegram group what we upload, we can see that. Okay, so this time period of oscillation is actually proportional to 1 by square root of gm actually. Now if you see, gm actually decides stability, but at the same time, let us suppose if the ship is a passenger ship, for example. Okay, in case of passenger ships, look, try to understand one thing. Time period of oscillation, let us suppose if this is the ship again. Now for one oscillation, what is one oscillation? Repeat one cycle, completion of one cycle. Okay, so let us suppose if the ship is like this initially, it tilts and come back to its original position. Okay, now whenever if you take for one oscillation, if you want the passengers to be highly comfortable, for one oscillation, time period of oscillation should be less or low, I mean less or high. If you want to keep the passengers at high comfort, the time period of oscillation should be high or less. It should be low or high. The passenger has to feel safe inside. Okay, he should feel comfortable. Then time period of oscillation should be high or low. I know all of you are telling low because of this. Okay, because I told you stability is proportional to metacentric height. So obviously you generally look for metacentric height. But as you keep on increasing metacentric height, what happens is this time period of oscillation becomes very low and passengers feel uncomfortable. Okay, comfort is different from safety. Okay, for safety, yes, 100% you have to increase your metacentric height. But for comfort, try to understand one thing. I'll explain you one simple thing. Look here. Let us suppose for one oscillation, the time taken is 10 seconds, for example, let us say. Okay, so what happens in 10 seconds, the ship slowly goes down and it slowly comes back. But now let us suppose the time period of oscillation is just 1 second. Then what happens? Within 1 second, the ship goes down and come up. Okay, so the rotation speed is fast. Then definitely the rotation speed is fast. Then definitely the passengers who are inside will feel discomfortable. Yes or no? Did you understand this logic? If the passengers has to feel comfortable, then definitely the time period of oscillation should be actually high. Clear? Is this clear to all of you? Simple. Okay, within 1 second if the ship is going and coming back to its original position, that means the ship is highly oscillating. Okay, then definitely the passengers inside will not feel okay. So in safety point of view, GM has to be very high, but in case of stability point of view, I mean in case of this comfort point of view, GM should be slightly compromised actually. So in passenger ships, what we generally do is, looking at the safety of the passengers and also in the stability, we will adjust it's like a compromise again. Okay, so it comes to a compromise of a value of GM. But in case of cargo ships, where generally stable comfort is not of much importance generally, and goods is of very high importance generally, then this is what you have. Clear? We actually keep high values of GM, metacentric height, so that it can maintain the stability. Okay, so is this clear to all of you? Okay, in L&T interviews, what's the question they ask you is, if I want to design a ship, what should be my value of GM? Okay, then you should say it depends on the type of the ship we are designing. For cargo, it is something different. For passenger ships, it is something different because of these logics. Okay, fine. Now anyway, let us solve one question, because this is before going for differential analysis, let us solve one small question before we go. Okay, so let us see this. The minimum apex angle of a solid cone, apex angle is basically this angle. Okay, so this angle is called the apex angle, that's called apex actually. So the minimum apex angle of a solid cone of specific gravity 0.8, so that it can float in stable equilibrium in fresh water with its axis vertical and vertex downwards actually. Yeah, okay, it can happen. Maybe it depends upon the type of places they visit for interviews and all. It's okay. Okay, yeah, obviously production manufacturing side, maintaining the ship and all is very important. Okay, materials they ask you. Now let us see the minimum apex angle of a solid cone of a specific gravity 0.8, so that it can float in stable equilibrium in water. So let us suppose there is a cone. You have a cone actually, but this cone is like with its axis vertical and vertex downward. Okay, so this is what? Axis vertical. So this is the axis of the ship. So this is axis vertical. So this is axis vertical and vertex downward clearly. Okay, so this vertex is downward. Let us suppose if this angle is theta, for example. Okay, so apex angle is 2 theta. Obviously, then this apex angle is 2 theta. Okay, because if this half is theta, then total apex angle is 2 theta. Okay, now let us see one thing. I think my cone got deflected only one side. Let us slightly pull this way, and let us adjust it in the middle. Oh, I think I'm not drawing a proper cone. Let us draw actually. Okay, fine. Okay, so let us suppose if this is the cone actually in this case, then fine. Now it's looking better, no? Much better. So this is theta actually. Okay, now if this is theta, let us suppose the water line is at this location, for example. Okay, so this is the water line actually. This is the water line, and obviously if you see the cross section, this cross section is actually circular. Oh, sorry, you have a circular cross section. Okay, so this is a circular cross section. Clear? So this is a circular cross section. Then let us see if this is a circular cross section, and this is the axis YY. Okay, so this is the axis YY actually. This is the axis YY. Now try to understand this. Let us suppose if this is density of the cone and this is density of the fluid, for example. Okay, we'll see solid cone of specific gravity 0.8. Okay, fine, we'll see this is OC and OF, for example. Okay, now this side is D. Let us suppose if this is diameter of the cone and this is the total height of the cone. Okay, till this point, this is the height of the cone actually. Okay, this is height of the cone. Then because of this condition, whenever this cone is actually floating in water, see what happens here. This depth of submersion, for example, say this is H, and at this point of submersion, let us say this diameter is D, small d. Okay, this diameter is small d. So this is small d clearly. Okay, that's small d, and this is height. Then let us see what should be the apex angle. Means basically if this cone is floating, what will be this apex angle? Okay, means it should be in stable equilibrium obviously. Then let us see to be in stable equilibrium. Okay, so now weight should actually balance the buoyancy force. First of all, this should definitely happen, yes or no? Because if the cone is floating, whatever is the weight of the cone, that should be definitely balanced by the buoyancy. Okay, now let us see here weight. What about weight? Density of the cone into 1/3 pi r square or d square by 4. Let us say pi d square h by 12 is the volume into g actually. So this is same as buoyancy, density of the fluid into. Now if this amount of cone is submerged in water, then pi by 12 d square h into g is what you can have. Yes or no? Is this equation clear to all of you? What is C? Didn't get this. C is cone. Okay, density is of the cone. Rho C is density of cone. Okay, so this is density of cone actually. Okay, we'll solve this question and then we'll stop this. Okay, because we have started slightly late, 10-15 minutes, 10-12 minutes roughly because of this issue. Fine. Weight is rho g. Yeah, weight should actually balance the buoyancy. So weight of the cone is density of the cone multiplied volume of the cone into g should be equal to density of the fluid into pi by 12 d square h into g actually. Yes? Yes or no? Please type in the chat box. Is this equation clear to all of you? If this equation is clear, then we'll move forward. Okay, fine. Now let's see certain things. G pi by 12 gets cancelled. So rho c by rho f is equal to d by d whole square into h by h obviously. Okay, so this is what you have. This is the equation. So density is equal to this expression. Both are dimensionless. Okay, so this is the expression d by d whole square into h by h actually. Okay, now let us try to understand one thing. In this triangle, if you see, for example, if you take these two triangles, for example, if this angle also is theta, this angle is also theta, can I say from this triangle tan theta is equal to d by 2 divided by h? Also tan theta is equal to d by 2 divided by h. Means can I say this tan theta is equal to d by 2 divided by h? This ratio is also same as d by 2 divided by capital H. Sorry, this is small h. This is small h actually from this triangle. Okay, so from these triangles tan theta is this, which means one thing I can say here, if you cancel 2 and 2, this d by d is same as h by h actually here. Okay, so this is what we can say, d by d is equal to h by h, and of course tan theta is equal to d by h, d by 2h, or it's also d by 2h. We'll use these expressions whenever it's needed, but for the time being, can we do one thing? This is small d by d capital square into h by h whole square. Since this small h by h I can replace with small d by d, because you can see small h by capital H I can replace with small d by capital D. What we can do? We can write that this density of the cone by density of fluid is equal to d by d whole cube is what we can write. Yes or no? So d by d whole cube. Now let us see first stable equilibrium. Metacentric height has to be positive. This means metacentric radius minus bg has to be positive. In the least limiting case, this we can, okay, this is actually positive. At limiting condition, what did they ask you? The minimum apex angle. Fine, so they're asking you for minimum. Okay, so minimum, so let us see, bm is actually greater than or equal to bg in the limiting case. Okay, so this is for limiting case. This equality sign is for limiting case. Okay, equal to 0 including limiting case means just when the cone is stable. Okay, so limiting case. Now what is bm actually? So we know when this cone is floating about this axis, bm is nothing but moment of inertia about this axis yy. Okay, so iyy is actually pi by 64 d power 4 by volume submerged. So what is the volume submerged actually? This is the amount of volume which is submerged. Yes or no? So pi by 12 d square h. Pi by 12 d square h should be greater than or equal to Bg. Now what about Bg actually? Look, normally if you have a cone, do anyone know what is the depth of centroid of the cone? Means if this is total h, this value is actually h by 4. Okay, and clearly this value is actually h by 4 actually from this surface. Okay, because that's the submerged portion. Now the main thing is, yeah, it's h by 4. Okay, h by 4 from the base of the cone. Okay, it's not h by 3, it's not a triangle, it's a cone actually. Okay, if you do the integration, we'll get h by 4. Okay, h by 3 is for triangle. Okay, h by 4 is actually for the cone. Clear? Now this is h by 4. The main thing is you should identify what is this distance, because this is a g and this is b, centroid of the displaced fluid actually. Okay, so what is this distance? How can you identify this distance actually? See carefully, we can easily identify this distance. This total distance is actually h minus h. Okay, so this is h minus h. Now can I say one thing? This h minus h plus h by 4 minus capital H by 4 gives Bg, correct? So Bg can be written as, look carefully, Bg can be written as this total distance, which is nothing but this capital H minus small h plus small h by 4. So capital H minus small h plus h by 4 is what you have, minus this capital H by 4 you have to subtract. If you do this calculation, then you are going to get this Bg. Yes or no? It's a geometrical thing. So capital H minus small h by 4, 3h by 4, small h plus 3h by 4 minus 3h by 4. So means basically you can say Bg will be actually equal to 3 by 4 times of h minus h. Correct? Can I say this? Can I write this expression for Bg? Yes or no? Type in the chat box. Yes or no? Quick. Please type in the chat box. Can I say this? Now this should be greater than or equal to 3 by 4 times of h minus h actually. Okay, now this is the condition. If you simplify certain things, okay, so pi and pi gets cancelled, obviously this d square will eliminate this d square times, and also we can see this is 12, maybe 4 table 3 times and 4 table 16 times. So 3 by 16 d square by h should be greater than or equal to 3 by 4 times h minus h actually. Okay, so this is what you have, and clearly you can understand one thing. Okay, d square by h is greater than or equal to 3 by 4 times of h minus small h actually. Then this cancel this 4 times, okay, and this 3 will cancel this 3. So we have d square by 4h is greater than or equal to, if you take h common here, we have h by h minus 1 actually. Okay, so this is capital H divided by small h minus 1 actually in this case. So if you bring this h here, this is like d by 2h whole square should be greater than or equal to h by h minus 1 is what you can write. Now what is d by 2h? D, this is small h, no, sorry, this is small h actually, because d by small d by 2h is what you have. So this is 2h. So d by 2h is actually tan theta. So tan square theta should be greater than or equal to capital H by small h. So what is capital H by small h actually? You can see this capital H by small h can be written as capital D by D, or this small d by d can be written as density of the cone by density of the fluid is equal to small h by capital H whole cube, because this ratio is same as this ratio, because you can see small d by d can be same as small h by capital H. So therefore this ratio can be written density of the cone by density of the fluid is equal to small h by capital H whole cube actually here. Okay, now if you use this equation here, this can be written as this capital H by small h is nothing but 1 by specific gravity whole power 1 by 3. Okay, so because this 3 if you delete here, this comes out to be 1 by 3 here. So capital H by h is nothing but density of the fluid by density of the cone whole power 1 by 3 minus 1 actually here. Okay, so that's what you have. So tan square theta should be this greater than or equal to this particular value. Now this term is nothing but tan square theta should be greater than or equal to, this is 1 by specific gravity power 1 by 3 minus 1. This is the condition for stability in this case. Okay, look, it's very simple. BG we have identified, we have cancelled certain terms. We have d square by h, 3 got cancelled. Then d square by 4h, we imported one more h from this taking common, and we have written d by 2h whole square should be greater than h by small h minus 1 actually here. So this is 1 by specific gravity whole power 1 by 3 minus 1. And in this case, definitely they have given you what is the specific gravity, because if this is water, then definitely density of the cone divided by this is specific gravity 0.8 is what you have. Okay, so tan square theta should be greater than or equal to 1 by 0.8 power 1 by 3 minus 1. So you can get the expression for theta. Theta should be greater than or equal to, let us calculate that value, 1 by 0.8 power 1 by 3, 1 by 0.8. Okay, so 1 by 0.8 power 1 by 3. Okay, so cube root of this. Okay, so cube root of this 1 by 0.8 of this minus 1 minus 1. So this is positive value. So take a square root of this. This is 0.2778. So tan theta should be greater than or equal to, how much is this expression? 0.2778. 0.2778. So if you take tan inverse by putting it in degrees, tan inverse gives you 15.529 degrees. So theta should be greater than or equal to 15.529 degrees. 529 degrees. But this is only theta. So theta should be greater than or equal to this. But apex angle, actually if you see, 2 theta should be greater than or equal to, if you multiply this with the 2, then 31.059. Okay, so 2 theta should be minimum of 31 degrees roughly. Clear? Yeah, 31.3. Chota question ka itna bada answer. It's not at all big if you see. If you clearly solve, this takes you 1 minute roughly, and this takes you 2 minutes. To explain you, I am taking some time, but if you solve this question on your own, you can see it's very simple configuration actually. Okay, so 31.059, roughly 31.1. Okay, this calculations can change the second and first decimal. So 31.12 degrees is the answer in this case. Okay, this is not a lengthy question actually. Okay, so you can solve this. I've solved this question because questions are very good now, obviously. Yeah. You can see in this case, identifying this moment of inertia for a cone is the toughest thing. This, if the toughest question in metacentric height comes out, this will be the question. Okay, and apart from this, you can solve all easy questions. You have a cuboid like this. Let us suppose if I give you questions like this. When I'm explaining the theory, I have given you certain things now, like this for example. If I give you these kind of questions, calculation, BG, all these things are very much easy, dead easy for you. Okay. Fine. So is this clear to all of you, everyone? So if it's clear, then we will maybe see the differential analysis in the next session, and we will stop here, because in this 2 minutes we have talked about buoyancy and flotation completely, and flotation we have solved completely, and we have also solved some problems regarding to the stability of metacenters, all these things. Okay, and for this stability of shift document, you can visit this group t.me. Okay, fine. Again, sorry for the delay in the start because of this unexpected update of the system, but yeah, I hope things are clear to you. Okay, fine. So we'll meet tomorrow morning and we'll see the differential analysis. We'll see the accelerations in Cartesian polar coordinates, then deformation of fluid elements, twisting of fluid elements and all, shear strain rates, shear stress tensors, all these things we will see. Okay. Yeah, because this topic got ended here today, I'm not putting any practice question, but tomorrow definitely we'll keep certain mathematical questions which gives you some good practice. Okay. So I hope all of you are learning something through these sessions. Are these sessions helpful to you? Are you all feeling these sessions useful or helpful to you? Are you all getting some benefit out of this? Today statics finished. Okay, so tomorrow we'll start differential analysis. Are you all learning any new points and feeling something good about knowing things? Much helpful? Okay then, so we'll continue then. Thank you all. We'll meet tomorrow at again 7:30 AM. Okay.
Yeah, thank you all. Take care. Bye.